Okay, good day, grade 10s. I trust that you are well. We are starting off with a new and exciting section called functions. Now, this is not entirely new to you because you looked at functions all the way back in primary school, right? You did something called a spider diagram, right? Or a flow diagram. For example, if I have a set of input values, as the name suggests, input is something that you put in. And if I have a set of output values, as the name suggests, these are the values that you get out at the end. Now, the way I like to think about a function, of course, it's just a relationship between the input and the output values. But the way I like to think about a function is that, let's say I have, let's get that out of the way. Let's say I have a car. Let's just say I have a random car, and this car is unwashed. Right, so I haven't washed my car in quite a while. And so if my car is unwashed, this is the input. So what I'm going to do is I'm going to take this to the car wash. That's sort of the process, right? If you looking at a more English term, the process. This is basically your function. It's it's what you are doing to the input in order to get an end result. And what is the process? Is that I'm going to wipe the car, uh, I'm going to water the car. Well, the other way, it makes sense if I first water the car. Let's just get this out of the way first. Right, okay. Right, so I'll first water the car, then I'll wipe down the car, and then I'll have foam on the car, and etc. Right? And what is the end result? It's a clean car. Right? So whatever I do to this input, I'm going to get a corresponding output value for that as well. And that's basically a function. A function states that for any input values, now we use the variable x. X is our independent variable, right? X is our independent variable. We put it through an equation of sorts, and we get our corresponding dependent variable. Remember, y represents the dependent variable. So independent variable is a variable that can stand on its own. It is not influenced by the dependent variable. Whereas the y value that represents our dependent variable, and as we learned in grade 8 and 9, and also all the way back in primary school, that the y value, which is the output, is basically the dependent variable, and that means that it depends, as the name suggests, on the x value, whatever the x value is. So function, you have to have one x value for one y value, or when we look at a parabola and other types of functions, you'll see that you can have one x value and two possible y values as well, but that's in the case of a parabola and other functions as well. But for now, the function that we dealt with uh, the function that we dealt with in grade 8 and 9 and thus far was the linear function. We looked at that in analytical geometry as well. But going back to my point that this topic functions, which is very, very interesting, it's not a new concept to you because when you were in primary school, for example, let's say we have these x values. Let's not make it. Let's increase it. Let's just say we have these random x values. Remember, x can be any real value. It can be a fraction, it can be 0, it can be an integer, etc. Then we have our process. What are we doing to this? Let's say first we are multiplying it by 2, and that product, we are adding 1 to that. So of course we don't need a calculator to get this. It's quite simple. Now this is of course primary school content. I'll take the x value, which is -1, and I'll multiply it to 2. So -1 times 2 is -2, and -2 plus 1, that's -1. So when the x value is -1, the y value is -1. When the x value is 0, 0 times 2 is 0. Anything multiplied by 0 is 0. And 0 plus 1 is 1. Then when the x value is 1, 1 times 2 is 2. 2 plus 1 is 3. 2 times 2 is 4. 4 plus 1 is 5. And as we learned in analytical geometry, specifically when we have x and y values, we can write it as a coordinate, right? The coordinate, any coordinate is always in the form of x, y. You first look for your x on your horizontal axis, which is your x-axis, and then you look up or down for the y value on your vertical axis. And let's just plot these, or let's just write out these coordinates. Well, we have it in the spider diagram. It's -1. I don't like this color. Let's choose this, right? It's -1, -1. The x value, when the x value is -1, the y value is -1 as well. When the x value is 0, the y value is 1. When the x value is 1, the y value is 3. When the x value is 2, the y value is 5. Now, of course, we in high school, we do not use the flow diagram per se. So we can write this out as an equation. What am I first doing to this x value? I'm first multiplying it by, so to get the y value, so I'm going to say y is equal to, the first thing I'm going to do to this x value is I'm saying x times 2. So as you know in maths, we don't write it as x2. We always write the coefficient first and then the variable. So it's 2x, which means 2 times x. And what property are we using to swap that around? The commutative property of multiplication. Then what am I doing to this product 2x? Because of course in board mass you first deal with the multiplication. I'm adding 1 to that product. And so this is my equation. Y is equal to 2x plus 1. So I'm going to substitute different x values to find corresponding y values. So for example, let's say we have the x value of 3. What am I going to do using this equation? I'm going to substitute 3 in the place of x, and I'm going to get my corresponding y value. And of course, in maths, whenever we make a substitution, we always make use of brackets. So it's y is equal to 2 in brackets 3 plus 1, which means 2 times 3 is 6 plus 1, which is equal to 7. And the coordinate here is 3, 7. When the x value is 3, the y value is 7. Now that's all good. Now this is an example of a linear function, right? And that is the first topic of discussion. We're going to open Sketchpad, so that's going to be exciting as well. And I'm going to show you the effects of, or the different parts of a linear function. So that's very, very, very fun. Okay. Now, as I was saying, the first type of function that we're going to look at, and this is not something brand new to you, is the linear function, right? The linear function. Okay, so that's our objective for today. I might need to make another, the second part where we look at the parabola, the exponential graph, the hyperbola, etc. But for the linear graph, I like to start off with this because we dealt with the linear function in the past and also in analytical geometry. A straight line, as with our example, y is equal to 2x plus 1 in the beginning of this video, a linear function is always in the form of y is equal to mx plus c. I've read other textbooks as well. They will write out the exact same equation as y is equal to ax plus q. Right? So don't get confused. It's the same, essentially the same thing. Now, the y value is, of course, the y value in our coordinate. The x value is the x value that we put into the function. But what does m mean? M is basically the gradient, right? Also A, if you're using the standard form, as I'm just showing you both because some textbooks write it as y is equal to ax plus q, or any variable, but it's essentially the same thing, right? The coefficient of the x value, that is the gradient. And as we learned it, that is m. Just a quick recap. How do we find the gradient of a straight line? Because by the way, again, with functions, we might need to find the equation of the line. So we, of course, we need the m value. Right, so to find the m value, it's always um, rise over run, right? It's always rise over run. Basically, the change in x, sorry, the change in y over the change in x. Do not make that mistake. You always start with the y value. So you just need two coordinates. Let's say y2 minus y1 all over x2 minus x1. And that will give you the gradient of the line. When we talk about gradient, we are referring to the slope of the line. So imagine that you get into school, right? And you have to walk up the steep the steep slope, the hill rather, right? So there you are at the bottom of, there you are here, and you want to get to school, which is on the top of this hill. Will you walk up or or are you walking down? Firstly, you walking up. This is an example of an increasing graph. I'll show you now on Sketchpad when we start sketching uh, coordinates, or rather linear functions, that with regards to an increasing graph, as the x values are increasing, the y values are increasing as well. And what we can observe of the increasing graph is that if the gradient is greater than zero, what does that mean? It means that if the gradient is positive, so if the gradient is 1, 2, let's say it's half, let's say it's 3/4, if it's positive, basically if it's not negative, then we have an increasing graph. And if our graph, if we have to, let's say we have to sketch this graph here, right? Let's say we have a graph that looks something like this, right? Okay, so there you are here, you're on the top of the hill, and now you want to get to this point at the bottom. You're going down, and if we have to look at the Cartesian plane with our x and y axis, we can see that as the x values are increasing, the y values are decreasing. So there's an inverse relationship between the two. When you look at, okay, I'm just jumping the gun here, so let's just call it a decreasing graph. But when you are studying economics, you'll learn about the supply and demand graph, and this is price and this is quantity. So the horizontal axis represents quantity, the vertical axis represents price. Now your demand, let's see if I still remember this. Your demand graph is your decreasing graph, and your supply graph is like this. And the point where these two graphs meet is what we call your equilibrium point. That was also quite interesting. And again, the maths applies to all subjects basically. So it's quite, I always enjoyed studying graphs in economics. Now, that being said, a graph is decreasing when the gradient of the graph is less than zero, when you have a decreasing graph. So that is basically the effects of gradient. We're going to do a nice, very fun investigation in a minute. But before we do that, let's just understand what does the C value mean. C represents your y-intercept, right? If you have forgotten from analytical geometry, let me quickly refresh your memory. Now, on the x and y axis, when I'm referring to axis, please note that I'm referring to the Cartesian plane. So remember, your Cartesian plane has two nice axes. It'll look much better on Sketchpad, which I'll show you momentarily. Right, but for now, let me just quickly draw a quick sketch. That looks quite nice, right? Okay, so let's say we have two axes, right? We have our x-axis, which is our horizontal axis, and we have our vertical axis, right? Now, this is what I'm talking about by the Cartesian plane. This point, by the way, if I have to draw the plot the coordinate 0, 0, this is what we call the origin. It's when the x and y intercept, x and y axis intercept. Now, when I talk about the x and y intercept, I mean, if I have to plot a point, if it touches this horizontal line, we call it the x-intercept, right? And when we find the x-intercept, you might notice what is the y-coordinate. The y-coordinate is always 0. So the golden rule is that to find the x-intercept, you let y equals to 0. So you substitute y into this equation. And if I plot a point and it touches the y-axis, it means that my x-coordinate is 0. So to find the y-intercept, we let x equal to 0, right? So I know what you probably thinking right now. You're probably thinking, right, what is the effects of m? Highly doubt it. You were thinking that, but let's just say the gradient of the line is 1. Then I draw another graph with the gradient is 2. Then I draw another graph with the gradient of 3. Then I draw another graph with the gradient 4. What effect does the gradient have? And also, likewise, if I have to decrease the graph as well. So what I'm going to do now is I'm going to open Sketchpad and I'm going to draw, we're going to investigate a couple of interesting linear functions. Now, the first thing I'm going to do is I'm going to plot the mother function, the mother linear function. Now, what is the mother linear function? Let's take this out. Right. What is the mother linear function? Okay. Okay. The mother linear function. Right. Mother linear function is y is equal to x. Now, this is a straight line function as well. Why? What is the m value? There's an invisible coefficient of 1. This means 1 times x. What is the y-intercept? What is the c value? It's 0. So this is the mother function, and what we're going to do is we're going to plot different graphs on the Cartesian plane, and you'll be able to see what's happening to the m and the c value. So let's just pause here, and then we'll go straight into Sketchpad. Okay, so let me just quickly stop. Okay, so we are now on Geometry Sketchpad, and just a disclaimer very quickly, I just want to apologize. I'm just trying to figure out the axis, right? So of course we have, as you can see on the screen, we have the x axis. The label should be somewhere to the right, and we have the y axis. Don't forget to label it as well. Now I'm just trying to figure out how to label this, because remember the axis is going 1, 2, 3, 4, 5, 6, 7, 8, and the software is just skipping some. And of course, this mark here represents 1, 2, 3, 4, 5. So I would have preferred if they actually marked it, and that's what I was trying to figure out at the moment. But nevertheless, it's fine. We can use it as is. But I want to quickly plot the mother function, which we know is y is equal to mx plus c, right? Which is y is equal to x rather. So let's do this. Right, let's plot y is equal to x, right? And remember, what is the gradient? The gradient is 1. That was the coefficient of the x value. So this is the function. So when x is equal to 1, y is equal to 1. When x is equal to 2, y is equal to 2. When x is equal to 3, y is equal to 3. When x is equal to 4, y is equal to 4. And x is equal to 5, y is equal to 5. So you get the point, right? So this is the example of the graph. Let me write through this cursor. I think that would be better. This is the graph y is equal to x. Remember, this coordinate, this is our x coordinate, this is our y coordinate. Well, I have the pen in my hand. I'll try not to move it, but remember, this is 1, 2, 3, 4, 5, 6, 7, and this is -1, -2, -3. Looks like a dot, but this is just okay. Never mind. This is -4, and you get the point, right? It's quite difficult to write this. 2, 3, 4, 5. This is -1. See, it's doing its own thing. think it's too close. Okay, never mind. You get the point, right? This is -1, -2, -3, etc. Just wanted to quickly show you that. But this is the graph y is equal to x. Now let's draw a new graph y is equal to 2x. Right, so now let's draw the graph y is equal to 2x. You might see they're calling it g of x. I'm going to explain the function notation with you in a minute. Okay, so let's draw the graph y is equal to 2x. Where's my graph y is equal to 2x? Just give me a second. Okay, there it is, right? So this is the graph y is equal to 2x, and let's label it as such, right? So this is the graph y is equal to 2x. I'm going to explain why do they call this graph g of x, right? This is how you read this symbol g of x, and I'll explain that when we go back to the board. So I can see that this is the mother graph. As you can see, the mother graph is, without causing too much of a mess on the diagram, this is the mother graph y is equal to x. The new function that I just drew was y is equal to 2x. What was the difference? The difference was, right, so this is y is equal to 2x. The difference was now that the gradient is 2. For the mother graph, the gradient is 1. Now let's draw another graph. Let's plot a third function, and let's make now g of x, or y, which basically means y is equal to 3x. Again, if you're a bit confused of what this is, I'll explain it to you momentarily, and you can come back to this part. The gradient of this line is now 3 as opposed to the mother graph of 1. Okay, now let's just draw one more graph. Actually, no, let's just draw for 2 more graphs very quickly. Okay, let's plot that function, right? This is the graph y is equal to 4x. And lastly, let's plot the last graph, which is 5x. Okay, so these are my graphs, right? Now you might look at it a bit confused, but this is the graph y is equal to x, y is equal to 2x, y is equal to 3x, y is equal to 4x, y is equal to 5x. If I assume if I have to draw the graph, y is equal to 6x, it's going to be somewhere here. So what's happening? The graph is much more steep. As the y values are increasing, the graph becomes more steep. Now, if you have to understand steepness, let's say you're going to school. This is you're going to school. Now, the school is at this point here. Now, this graph, this is quite steep. You have to walk uphill. Now, imagine that to walking you here, and the school is now here. Which is option 1, and I have option 2. Which one looks more steep? Definitely option 2. And that's what's happening. It's getting closer and closer to the y-axis. So as the m values are increasing, the y values, the graph becomes more and more steep, right? And if the graph is a horizontal flat line, it means that m is equal to 0, and that the graph is not steep at all. Now, let's just draw an example of this graph, not to confuse you too much because there's a lot going on. Actually, let me delete. Let me do this. Right. So let's just draw a horizontal line. Let's draw the graph y is equal to 2. This is the graph y is equal to 2. And as you can see, this is just a flat horizontal straight line, meaning that there is no gradient. It's like when you are driving on a road and it's a straight road, right? It means that there is no gradient to that road. So it's just, or you're walking on a straight surface, right? So that was the effects of M. So now what we're going to do is we're going to quickly go back to us, our work. But before we do that, the effects of C is basically our y-intercepts. So that's going to shift our graph vertically. But we are going to go back to our board, and we're going to discuss in detail what do I mean by g of x, h of x, q of x, etc. This is slightly new, but we will look at it momentarily. So let's go back. Okay, so welcome back to our board. Now we're still on linear functions. I think for this part we'll just discuss linear functions because it's quite time consuming, and then we'll look at the parabola in the next video. But we just came from Sketchpad where we looked at the function y is equal to mx plus c, and we said that the greater the value of m, the steeper the graph, right? So you might notice that we do not call the graph y is equal to something. We rename it according to its functional notation. Now there's two ways, functional notation, right, like that. Right, now there's two ways I can express the graph. I can write it in the form of map the graph, or I can write it off. So let's do the first one because that's the most common. Now let's take the function y is equal to 2x plus 1. This is the function we used in the beginning of the lesson, so I think it's only fair that we use it again. Now in high school, specifically in FET grade 10, 11 and 12 and so forth, you know the y value to be y, but to differentiate it, we can give this graph a name. We can call it f of x is equal to 2x plus 1. Now, as I said it, that's how you read it. You read this as f of x is equal to 2x plus 1, right? That's how I read this. Now, you don't have to call it f of x. You could call it g of x, or you could call it h of x, or you could call it s of x. Now, there's different names that you can give it. Now, let's just call it f of x. F of x, this represents my y value. It's just a fancy way of saying y. Whenever people see f of x, they start to panic, and I don't know why, because it's just y, right? So let's say, for example, we have f of x is equal to 2x plus 1, right? And I say that, actually I have an example here. I say that the x values, this is quite interesting. I say that the x values lie between and are equal to both -3 and 2, right? And x is the element of integers, right? Integers, of course, we know what an integer is. It's, for example, 0, 1, 2, 3, and the negative versions of that, -1, -2, the negative versions of those whole numbers, right? So, or the natural numbers. Now, what we can do is to plot a graph onto the Cartesian plane. The method that I taught you, or you should have learned in primary school, was the table method, right? So, for example, if you have a table, I'm just going to be a bit quick here because this is just a recap. I have my x values and I have my y values. Now, they said it's -3, -2, -1, 0, 1, 2. So that's how my table looks. If I have to draw a quick table, right? It's not the neatest, but this is how my table looks. And we learned how to plot a graph. We need our x, y coordinates, so you can just draw a table, and they gave us the instructions for that. Now, when x is equal to -3, what's the y value? So what we're going to do is we're going to say f of -3 is equal to, what this basically means is that I'm going to substitute -3 in the place of x. So I have 2 into -3 plus 1. That's equal to -6 plus 1. That's equal to -5. So when the x value is -3, the y value is -5. We can do the same. We can say f of, when the x value is -2, what is the y value? What's the corresponding y value? So we say f of -2 is equal to 2. I'm going to substitute -2 in the place in brackets. So that's -4 plus 1. That's equal to -3, right? And you can do the rest likewise. I can say that 2 times -1 is -2 plus 1 is -1. 2 times 0 is 0 plus 1 is 1. 2 times 2, 1 times 2 is 2 plus 1 is 3. And then I can say that 2 times 2 is 4 plus 1 is 5. And then I can get these coordinates and I can plot them onto the Cartesian plane. Now, what if, I wish I drew this table much more neater, but nevertheless, what I can do is just take away all this. Okay. So let's get this here. Let's say I extend the table a bit. Okay, let's say I extend this table. It's not the neatest table, but let's just say I extend it a bit, and there's some space here and there's some space here. Now, let's say I tell you that the y value is 11, 21. What is the x value? Let's call it m, right? Because we do not know it. And I ask you to find the value of m, to solve for m. So to find m, we know that the equation is f of x is equal to 2x plus 1. F of m is equal to 2. Now I'm going to substitute m in the place of x because that is our x value. It's the variable m. Now we need to find m. Do we know the value of f of m? Yes, that is our y value. It's 21. I'm going to say 21 is equal to 2m plus 1. And all I can do now is just solve this simple linear equation. I'm going to take 1 to the other side, so it's 2m is equal to 21 minus 1. 2m is equal to 20. Divide both sides by 2. M is equal to 10. How do you interpret that? You basically interpret that as f of 10 is equal to 21. Right? When the x value is 10, the corresponding y value is 21. So that's method 1, right? This is one of the methods on how you can plot a linear function, not even a linear function, a parabola, a quadratic function, or hyperbola when you get to grade 12, a cubic function, etc., onto the Cartesian plane. You can just simply draw a table. And by the way, the Casio calculator can also, they can give you the coordinates there, but we'll look into that a bit later on. But for now, you can just apply the table method and you can draw your graph. But that's quite, and I'm going to be quite honest with you as well, it's very time consuming to use all those points, because to be honest, you do not need all those points to plot a point onto the to plot a graph onto the Cartesian plane. All you need is a minimum of 2 coordinates. You just need 2 coordinates. That's it, right? So that is why the easiest way to plot a graph is to use the dual intercept method. And I think I alluded to this earlier in this video, right? The dual intercept method, all you need is the 2 intercepts. You need your x-intercept and you need your y-intercept. So once you have those 2 coordinates, those 2 intercepts, you can just take your ruler and join those 2 lines together and you have your function as well. Do not forget to label your function, right? Like what we have been looking at on Sketchpad, whether it's f of x, g of x, etc. So I think I can quickly go on to Sketchpad here. Right, let's just quickly go on to Sketchpad. I'm not too sure if it's too clear, right? Because some of the graph is cut off on the top here. But always label your graph. For example, if this graph is f of x, you label it f of x. So that differentiates it from this graph, which is y is equal to 2x, which we will call g of x. So we will call g of x. And then this graph we can call h of x, and then q of x, r of x, and so forth, and so on. So that's basically what we have. So the dual intercept method, just to get back to the point, you need the 2 coordinates. You need your x-intercept. Just to recap very quickly, you let y equals to 0, and then you get your coordinate in the form of xy. And of course, I know what the y value will be, 0. Then I find my y-intercept, and I let the x value be equal to 0. And of course, again, I know what my x coordinate is going to be. It's going to be 0, and whatever y value. Once you have these two coordinates, you can draw a straight line, and you have your graph. Now, the last method, now this is the method that I did not use at all, but nevertheless, I'll just quickly explain it to you just in case you are interested in this. And I think the more methods you know in maths, the more comfortable you are. So this is the method that is called the gradient intercept method. Right, so I hope I can do justice to explain this to the best of my ability while drawing a quick sketch of it. But it's also quite interesting. Like, for example, right, uh, let's do an example. Let's call it example 1. Right, and I think we can probably end on this note. But let's say we have to sketch the graph of f of x is equal to 3x plus 2. Again, this is a way of saying y is equal to 3x plus 2 using the gradient intercept method. Right, now, again, to be honest with you, I personally prefer either the table method or the easiest, the Joule intercept method. But nevertheless, let's just use it. So we need one coordinate to start off with. So we want to sketch this graph. Again, when they say sketch, try to use a pencil and a ruler and make sure it's as accurate as possible. I'm not going to do that because it's very difficult to actually measure on this board, but where in your notebook or in the test, use your pencil and ruler and make sure that your graph is as accurate as possible. Now, looking at this graph, we just need to start off with 1 point. So let's start off with the y-intercept. So number 1, let's use the y-intercept. Right now, I just explained this to you, I think, a couple of seconds ago, that to find the y-intercept, you let x equals to 0. Let's use the y-intercepts, and we need to let x equals to 0. So f of 0 when x is 0, so I'm substituting 0 in the place of x. So whenever I see x, I'm going to substitute 0 in the place in brackets. So 3 times 0 plus 2, which is 0 plus 2, which is 2. So what is the coordinate of my y-intercept? It's 0, 2, right? Now remember, the gradient is the change in y over the change in x. Basically, what your gradient is basically equal to rise over run. Rise referring to your vertical axis, and run, you run horizontally, right? Nobody runs on the wall, you run on the ground. So let's start off with a quick sketch, and I think we're going to end on this note. Then we can look at the parabola in the next video that's coming up, right? And then the exponential graph functions is not a very difficult section. As I said, it's a very fun section as long as you understand how these graphs actually work. And then we're going to look at concepts such as the domain and range of the graph, which is also interesting. They will ask you questions: where is the graph increasing and decreasing? And it's very, very interesting as well. And when we get to the hyperbola, the exponential graph, etc., we will look at the asymptotes, right, of those graphs, which seems like a very complicated word, but it's actually absolutely simple. And all you need to know is that the graph never touches the asymptote. But we will get to that when we cross that bridge. But that being said, I want to quickly draw a quick sketch of this. Now I'm going to draw it very small because just to save some space. 1, 2, 3, 5, 6, 7, what is it? -2, -3, -4, -5, right? Let's make this nice and small. 1, 2, 3, 4, 5, 6, 7, 8, -1, -2, -3. Okay, so you get the point, right? So this is a quick, very small sketch. Again, as I said, I'll prefer that you use a pencil and ruler. It's much more neat. Right, so what I'll actually like to do, now if I think about it, let me zoom into this because it's very, very small. Let's do this. Why is this doing this? Okay, scroll down. Okay, that's more or less visible. Again, it's a very small sketch, so I just zoomed it up. If I look at this graph, let's plot the point. So we said we have one coordinate. If you have forgotten, we found that the y-intercept was 0, 2. So let's start with that. When the x value is 0, the y value is 2. That's our first coordinate. Right. Now, gradient basically, it tells us the change in y over the change in x. So if I have to calculate the gradient of the line, what is my equation? Right, again, if you have forgotten, the equation we are dealing with is y is equal to 3x plus 2. So what is the gradient? Without even calculating the gradient, we can see that the gradient is 3. Y is equal to 3 over 1. So 3 represents our rise, whereas 1 represents our run. So as the x values, remember the denominator represents the change in x. As the x values are increasing by 1, the y values are increasing by 3. So when now currently the coordinate is 0, 1, the next coordinate is going to be 1. Now I said 0 plus 1 gives me 1. 2 plus 3 gives me 5. So it's 2 and 5. That's my second coordinate. Then the next coordinate, remember the run, let's start with the run, the x coordinate first. When it increases by 1, 1 plus 1 is 2. 5 plus 3 is 8. So it's going to be 3 and 8. And what you can see here is that basically I'm calculating the change in y over run. Now, again, this is a very rough sketch. I doubt that it'll be too accurate as well, but it should be more accurate in your notebook as well. And of course, wherever that x intercept is, I can't recall. So let's just say something like that. Do not forget, do not leave your graph inside the Cartesian plane. Try to extend it as much as possible, because remember, this graph is going all the way to positive infinity and all the way to negative infinity with regards to the y-axis. And do not forget to label your graph as well. So this graph is nicely labeled as f of x. You don't even have to write the full equation, it's just f of x. Right, so these are the three methods on how you can draw a straight line. Either the table method, the dual intercept method, which is regarded as the easiest method, or lastly the gradient intercept method, right? So that basically sums up functions. Of course, this is not limited to two. This is not the only concepts on functions. There's other things as well. I did not touch on how to find the equation of a straight line that we looked at in analytical geometry, and we'll deal with in class as well. But please just go over the work that we looked at, especially in analytical geometry, and how it integrates with the linear function when we plot it onto the Cartesian plane. Okay, thank you everyone for watching this video, and all the best with your future studies.